So we're looking at solving our area under the curve or area of the function problems. And we're given our first one as f of x equals negative x plus 5 over the interval from 0 to 4. Let's first look at this as if we have four rectangles to find this area. If that's the case, each one, since I have an interval of 4 units, is going to be 1 unit wide. So if I sketch this, there would be my 4 rectangles that I have. So my area is going to be the base times the height of each rectangle that I have. So each rectangle has a base of 1, and then its height is going to be the coordinate that I have for that in the function at each point. So I have 1, 2, 3, and 4. So I'm going to do f of 1, so that's the first rectangle, base width of 1, height of f of 1, plus 1 times f of 2, plus 1 times f of 3, and then plus 1 times f of 4. So the ones are all there, so I'm just going to, it's multiplication, so I'll just drop them off, and I'll look at just plugging into the function. So f of 1 is going to be negative 1 plus 5. F of 2 is negative 2 plus 5. F of 3 is negative 3 plus 5. And f of 4 is negative 4 plus 5. And that's just plugging in the values for 1, 2, 3, 4, and then negative x plus 5. So I get negative 1 plus 5 is 4. Negative 2 plus 5 is 3. We get 2, and the last one is 1. We add all of these up, 4 plus 3 plus 2 plus 1, and we get 10. So the area, when we have 4 rectangles in this, is 10 units squared. Now this is just an approximation. We could even see in doing those rectangles we have that extra space there, but it's a place to start. So next, let's take this if we had 8 rectangles. So I'm going to break it up into 8 parts. Now, all of the bases are going to be the same width. They're all going to be 1/2, as with the first one, they're 1s. So instead of writing out the 1/2s for all of them, I'm just going to put a 1/2 out front. And now I'm going to just write, it's going to be 1/2 times each of the f of the stops that I'm going to have. So before it was every 1, now it's going to be every 1/2. And what I actually have here is my rectangles. Let's clear these out. Or every half unit. About there. Right here. So now we're starting to see these rectangles are skinnier. They do have a width of 1/2. There's more of them, and we can actually see for an approximation sense they are getting closer to that line. So it's going to be 1/2 f of 1/2 plus f of 1 plus f of 3/2 plus f of 2 plus f of 5/2 plus f of 3 plus f of 7/2 plus f of 4. Bring down my 1/2, and now I'm going to plug in to each of my functions the negative x plus 5. So we get negative 1/2 plus 5. We get negative 1 plus 5. We have negative 3/2 plus 5. Negative 2 plus 5. Negative 5/2 plus 5. Or negative 3 plus 5. Negative 7/2 plus 5. And the last one is negative 4 plus 5. Now I'm just going to get the whole number ones knocked out of the way. So I have the 1/2. If I do negative 1 plus 5 is 4. Then I have the negative 2 plus 5 is 3. Negative 3 plus 5 is 2, and negative 4 plus 5 is 1, so that kind of knocks these out. We look at our fractional ones, and we have to remember 10 or 5 in halves would be 10 halves. So negative 1 half from 5 would give us 9 halves, which takes care of this one. Negative 3 halves plus 5 would be 7 halves. Then I have 5 halves, 3 halves, and those are my 4 there. So all of them are taken care of. Now combining these, combine the whole numbers. 4, 3, 2, 1 is 10. For my halves, 9, 7, 5, and 3, that's going to be 24 over 2, which is 12. So I have 1 half 10 plus 12, which is 1 half of 22. So we get an area that is now 11 units squared, which is a little bit more than the first one. We had 4 rectangles, so it is getting closer to be more accurate. So now, once we have that one, what if we had an infinite amount of rectangles? So for this one, I'm going to make some space here. And this is where we're going to use the limit for our function. So we're going to go the limit as n goes to infinity of the sum of I equals 1 to n. Now the first thing is going to be f of the width of our interval. The width of our interval is 4 units, so that's going to be 4I over n. And I take that from the definition that we have in the equation. What's nice is if our interval is from 0 to some value, you just take the distance from that value, because really it's how far it is, but we started at 0. If it didn't start at 0, it would be a little more complicated. We can get to those later. And then it's going to be 4 over n. So now I'm going to move the 4 over n in front of the sum, because it is not affected by the sum, because the sum has to do with I. And then that's going to be f of 4I over n. Now I'm going to put that into the function. The function we said was negative 4I over n plus 5. I'm going to rearrange some things here. I'm going to make this negative 4 over n times I plus 5. Now, whenever we have a sum with I or a constant, we're going to change them a little bit. So what they become, the negative 4, actually we drop the sum, so the negative 4 over n, and then I just becomes let me find my equations here. It becomes n squared over 2 plus n over 2. That's what I becomes. And then 5 becomes 5n. And that's what happens when we drop the sum. That's the sum formulas that we have, kind of a shortcut for us. We will bring down this 4 over n, even though we're not quite to that yet. Still working within the bracket. I'm going to distribute out the negative 4 over n to each of those two terms. That's going to give me a negative 2 on top and an n on top. And then with n plus 2, it looks to me like I just left with a negative 2 and then plus 5n. Now I can kind of simplify these together, negative 2n and 5n. I'm just going to make that into a 3n out in front. So I have 3n minus 2. Bring down the 4 over n. Distribute that in. 4 over n times 3n leaves me with 12, and then minus 8 over n. Now, I've done all this. I bring down now my limit, and I've actually done pretty much all the work. The final step is actually pretty easy, because now the limit as n goes to infinity, well, 12 is going to come out to be 12, because it's not affected by n. It's just 12. Now, 8 over n, when it has that denominator there, it's going to get rid of it, because as n goes to infinity, as it gets very large, 8 over n becomes 0, so the answer is 12. So how does that compare to what we had? Well, with 4 rectangles, if you remember, we had an area of 10. With 8 rectangles, we had an area of 11. If we had an infinite amount of rectangles, as the number of rectangles approached infinity, we get an area of 12 square units. So let's do another one. Let's take the function now 16 minus x squared. We'll do the same interval. And if we think of 16 minus x squared, that is a parabola going down. It's going to hit at 4. So our rectangles, we sketched them out for 4 rectangles, would be every unit. Now, what we notice here as I start to sketch that is what actually happens in my last interval is it looks like it doesn't have a height of at all, because at 4 the function is 0, and we're going to see how that affects it. So, graph aside, if I said 4 rectangles, we know our interval is from 0 to 4. So I'm going to use the points 1, 2, 3, and 4. So my area is going to be 1 is my width for all of them. I can just put that out in front. Then it's going to be f of 1 plus f of 2 plus f of 3 plus f of 4. And really we are distributing out really the width of all of them, but we want to just find the heights, put them together, multiply by the width. So f of 1 is going to be 16 minus 1 squared, which is just 1. F of 2 is 16 minus 4, or 2 squared. F of 3 is 16 minus 9, or 3 squared. And f of 4 is 16 minus 16, which was 4 squared. So what I get here, with the 1 out in front, is 15 plus 12 plus 5, not 5, it'd be 7, and 0. So together, looks like we have 15 and 12 is 27, plus another 7 is an area of 34. Now, that was 4 rectangles. Let's take a look if we had 8 rectangles. So now our interval is from 0 to 4. We use the ones we used previously, but we're also going to do the halfways. So I get 8 intervals. I got 1 half again, 3 halves, 5 halves, and 7 halves. And when we do our area, we're going to just take a 1 half and put it out in front, because that is the width of all of them. We are multiplying all of them by their height. So I have f of 1 half plus f of 1 plus f of 3 halves plus f of 2. Really just filling them all in. To here. Okay, now we put them in our function. So we're going to go 1 half. That's going to be 16 minus 1/4. That's 1 half squared. Plus 16 minus 1 plus 16 minus for 3 halves squared, that's going to be 9/4, plus 16 minus 4, that's 2 squared, plus 16 minus, this is going to be 5 halves, which is 25 over 4. Then we have 16, next one is 3, so that's going to be minus 9. Next we go 16 minus 49/4. And then the last one, 16 minus 16. Now off to the side, real quick, if I had 16, that's going to be 64/4. I'm just going to use that to help me through this. So we got 1 half in our lead. So 16 minus 1/4 is going to be 64 fourths minus 1/4, which is really what I'm doing right here. Just don't want to have to write that step again. So that's going to be 63 fourths. 16 minus 1 is 15. We're here at 16 minus 9/4. That looks like 55 fourths. Next term is 12, 16 minus 4. Next we go 16 minus 25 fourths. 25 from 64. It's 39, so that's 39 fourths. Then we go 16 minus 9 is 7. 16 minus 49 fourths will be 15 fourths. And then the last one is 0, 16 minus 16. So together, the whole numbers, I have 15, 12, and 7, which is 34. Then for the fractions, if I add all the tops, looks like I get 172 over 4, which 172 over 4 becomes 43. I can combine those and I get 1/2 of 77. So we can either write that as 77 over 2, or that looks like 38.5. So that's our area with 8 rectangles. So compared to what we had in the first one we got 4 rectangles, we had an area of 34. Now we're at 38.5. Let's go now to if we had an infinite number of rectangles. So this one's going to be the limit as n approaches infinity of the sum of I equals 1 to n of f of 4i over n times 4 over n. I'm going to move 4 over n in front of the sum, put in the function, that's 16 minus 4i over n squared. Now I'm going to work on the sum. Looks like I'm going to go 16 minus 16 over n squared I squared. And I'm doing that because I want to get I by itself, because I'm really just going to replace it when I bring in the sum. Or get rid of the sum, I should say. Now we'll get rid of it. 16 becomes 16n minus 16 over n squared comes down. I squared from our formulas becomes n cubed over 3 plus n squared over 2 plus n over 6. Now I'm going to distribute out, so I'm trying to simplify down here. If I distribute in 16 over n squared to each term, I get 16 over 3n plus, that'll be 16 over 2, or 8, and then 8 over 3n for the last one. Now I could combine the terms here. I'm not going to do that just because I have 16n minus 16 over 3n. I'm just going to bring down the 4 over n first, distribute that in. I now get 64 minus 64 over 3 plus 32 over n plus, that'd be 32 over 3n squared. Now the limit comes down, kind of forgot that, and that's as n goes to infinity. Now hopefully you're starting to notice whenever we get these fractions with n on the bottom, they're the ones that we're going to get rid of. After we get rid of the sum, after we distribute it in the 4 over n in this case, when we're left with whole numbers, that's what our answers are going to be. The ones without the n's are the ones that are going to survive after the limit of n to infinity is taken. So that's what happens here. These two are gone. I'm left with 64 minus 64 over 3. And what we get here is the 64 minus 64 over 3 is about 21 and a third. Well, it is 21 and a third. It's about 21.3. And so when you subtract that off of 64, we get to about 43 and 2/3. Or we could say about 43.7 units squared, and that's going to be our area with an infinite amount of rectangles. So this one had quite a bit more to jump. We went from 4 to 8 to the infinite amount, but it gives us that better approximation of what the area under the curve is by using rectangles.